We're going to take a look at Chapter 5, Section 4, which is all about irrational numbers. And so we're going to do a couple things. We're going to define them. We're going to simplify radicals that lead to irrational numbers. We're going to work on multiplying and dividing square roots, adding and subtracting them, rationalizing a denominator, and using a calculator with irrational numbers. So the first thing is, what is the irrational number? Irrational numbers are numbers that can be written as a decimal, but they don't ever end or repeat. So, for instance, the number pi doesn't repeat digits behind that decimal. And by repeat, I mean like something like 0.363636 is that rhythm. And the example here, also you can see it doesn't repeat any type of pattern. So then see. See if I can look at this. Originally, I was like, oh, this might be a pattern here because I have a 1 and a 3. But it's 1, 0, 3 here. It's 1, 3 here. So if you thought maybe you saw the pattern starting to repeat towards the end, it's not repeating. So these are super tricky situations. So what we do there is we say, well, there doesn't appear to be any type of pattern here. So it looks like it's an irrational number. So this definition may not be new, or it may be something that's a bit further back in your math education journey. There's one big section of irrational numbers, and those are square roots that aren't perfect squares. So for example, 2 is not a perfect square, so the square root of 2 is actually irrational. The same would be true of the square root of 3, square root of 5, square root of 7. So all of those numbers that are not perfect squares that give you decimal answers generate an irrational number when you're taking the square root of them. So a lot of times we've used the word square root a lot in your math journey, but the actual appropriate term is a radical. An expression with a radical symbol is a radical, and the number underneath it is the radicand. So for example, the symbol square root of 2 is actually having, instead of saying the square root of 2, we would say the 2 is the radicand, because it's under the number, and it's the radical sign. So we tend to read it as a square root, but the proper terminology here is going to be the radical and radicand. So the square root of a number, which we show as the square root of a, is a non-negative number that you have to multiply by itself to get a. So that's a long explanation. What it means is, if I have the square root of 4, 2 times 2 is 4, so the square root of 4 is 2. 3 times 3 is 9, so the square root of 9 is 3. So when I'm doing the square root, it's like backwards thinking through your factorization and saying, what are the factors of 9? Are any of those factors a number times itself? And those numbers are called perfect squares because they nicely simplify underneath a radical. So what do I do when I multiply square roots? So just like we can multiply variables, square roots have their own set of arithmetic rules. So if I multiply two radicals, then I can write them underneath the one radical sign and just multiply the values. So let's see how that actually works in an example. So if I want to simplify each radical, I'm not actually going to be finding a product here, so you're probably thinking, why is this slide related to the previous slide? And it's because in order to simplify a radical, I have to use that product rule. So when I simplify a radical, I want to write the number 40 as the product of at least one perfect square. So if I go through the factors of 40, 4 times 10 is a factor of 40, and 4 is a perfect square. So showing all the steps that probably were not shown in your high school math classes, that becomes the square root of 4 times the square root of 10 as two different radicals. Utilizing this rule here, I can write them as separate radicals. Oops. And so the square root of 4 is 2, so this becomes 2 square root of 10. I can't break square root of 10 down into any perfect squares, so that's as far as I can take it. So that's how I know I'm done with that section of the problem. In this one, we have the square root of 200. And so what can happen here is students will write the square root of 200 as like 4 times something. You want to try and get the biggest perfect square number you can get. So the biggest one I can get is 100, and 100 times 2 is 200. So I'm going to break it out and show that middle step. This is really important for students to see this middle step because they don't understand where this comes from if they don't see it as the product of two separate radicals. So it's going to be 10 square root of 2. And then from our previous sections, the prime factorization of 26 is 2 times 13. There's no perfect square number that 26 is divisible by, and there's no factor of 26 that is a perfect square. So that's as far as I can take it, and it's already simplified. And that's really important to recognize when something is actually done being simplified. So this is the problem that I really run into often with higher level math students is we have this product rule and we're like, oh, the product is just the radical times the radical. So then the sum would just be the radical plus the radical, and that's not true. So spoiler alert, that won't work. So if I look at the square root of a plus b, so let's say that b is 9 and a is 9 and b is 16. So I get the square root of 9 plus 16, which is the square root of 25, which is 5. So that's operating underneath one radical. What happens if I split it out? If I split it out, I get the square root of 9 separate plus the square root of 16, which is 3 plus 4, which is 7. So those are not equal statements. So that's a place students really get caught a lot. So let's do some practice with working the bulk product rule backwards. So if I'm looking at the first one, square root of 6 times square root of 2, the product rule says we can put it underneath one radical. So when I do that, what's interesting is I get the square root of 12, and the square root of 12 is not considered mathematically correct because it can be simplified. How do I know that? The square root of 12 is divisible by 4, which is a perfect square. So I have to actually break it down into 4 times 3, square root of 4 times square root of 3, and then my final answer that's fully simplified and mathematically correct is 2 times the square root of 3. This is a place where the best way to help your students with simplifying square roots is to have them memorize the perfect squares up to at least 100. If you know the perfect squares up to 100, so you know your 4, your 9, your all those different perfect squares, then it's going to better equip your students to think of, oh, can I divide it by 4? Can I divide it by 9? Can I divide it by 25? Can I divide it by 16? So that's how you're going to help your students get through this step. In part B, I have another interesting situation because I could break out the square root of 20 now and simplify it now, but that's going to make it really complicated for students. So I tend to say, go ahead and do the product to get the square root of 100, and then it's 10. If I took the time to break out the square root of 20 into 4 times 5, it would take a couple of extra steps. So the best thing to do here is just go ahead and do the product. And then in C, we have 2 times 3, which becomes the square root of 18, which is divisible by 9. So I'm not actually done with this problem until I break it out as the square root of 9 times 2, which gives me 3 square root of 2. In this case, it could have been easier to notice the square root of 3 times the square root of 3 is 3, because that would be square root of 9, but not all students are going to catch that. So the chances are, if you show this example to your class, a couple students are going to be like, raise their hand and say, well, can I just do the square root of 3 times the square root of 3 is 3? And the answer is yes. But not everyone is going to see that pattern easily. The quotient rule works very much like the product rule. I am able to just break it out into 2 separate radicals. The only thing that's an issue is that the square root at the bottom cannot be equal to 0. So that's an important rule that becomes important later in algebra, not necessarily at this point. So if I want to use the quotient rule, notice how these are separate roots. So what I'm going to do is gather them underneath the same root. And when I do that, 27 divided by 3 is 9, and 9 is a perfect square, so I get 3. Here I take the 2 separate roots, I write them together under one root, and then I get the square root of 12, which breaks down into 4 times 3. So how I got here was the square root of 4 times the square root of 3, and the square root of 4 is 2. Now, if you remember like terms with working with your variables, we also have what we call like radicals. So in an expression like 10 times the square root of 5, 10 can be our coefficient, and the square root of 5 can operate like a variable. So if two radicals are identical, other than the number in front of them, we call them like radicals, just like 2x and 5x are like terms. So examples of this would be 10 square root of 5, 7 square root of 5, negative square root of 5. All of these are like radicals, and like radicals can be combined just like terms. So here are some rules for combining like radicals. This is probably looking confusing, like you're doing some FOIL. You're not. What this says is if they are like radicals, just add the coefficients. Just subtract the coefficients. So seeing this in a concrete example is usually what makes it click. So if I have this here, think of this as 6x plus 8x plus 5x. We already know how to do that. When I do that with the terms, I just do 6 plus 8 plus 5. It's the same process with the like radical, because every radical is the same value and the same root. I'm just going to do 6 plus 8 plus 5, which is 19. So it's no different than combining like terms. It's just instead of having an x, you're going to have a radical. So here I have square root of 10. So 3 minus 7 is negative 4. Now, you can't have a negative under the radical, but it is perfectly okay to have a negative in front of the radical. Here, if I'm adding and subtracting roots, think of this as a little bit of a like term, because I need to break down 12, 8, and 32 because they're all divisible by a perfect square. So if I break out the square root of 12, you leave the 4 alone, and I get square root of 4 times square root of 3. The square root of 4 is 2. So I'm still leaving that 4 out front that was here. So this 4 here is why this 4 is also here. Then I took the square root of 4, which is 2, and now I have 4 times 2, square root of 3, which is 8 square root of 3. Here I'm going to do the same thing. I'm going to leave that 3 out front. I'm going to write 8 as 4 and 2. I'm going to take the square root of 4, which is 2, and then multiply it by the 3 that was out front. So I get 6 square root of 2. I'm going to do the same thing here. The 5 stays out front. Square root of 16 is going to be 4, so I get 20 square root of 2. So what you should notice here is you have two like terms, but the third one is not like, and that's okay. So I'm going to rewrite the problem out as 8 square root of 3 from here, 6 square root of 2 from here, and 20 square root of 2. Because these are both square roots of 2, they are considered like terms. So I can do negative 6 plus 20, which is 14. So that's where that 14 comes from. The 8 square root of 3 I can't combine with anything, so it's just still there. And then this is the fully simplified like terms of that. Now, rationalizing a denominator is often where we have the most issues with students. When we have a fraction, the denominator cannot contain a square root. That's not considered fully simplified. So if I look at these two examples, they both have square roots in the denominator, and that's a problem. So how do we rationalize the denominator? Well, the way that we do it is we multiply the fraction. So here's my whole fraction, and I'm going to multiply it by the denominator. So square root of 3 over square root of 3. Why do I do this? Because if you multiply any radical by itself, it's going to generate a perfect square. So at the bottom, I get square root of 9, which is 3. And so I no longer have a radical in my denominator, and very conveniently, I can break 18 divided by 3 into 6. So in the second one, you're going to do the same thing. You can't have a radical in the denominator. And so what they did was multiply by square root of 2 over square root of 2. Here's the thing, guys. Most of your students are not going to understand this step. They need to multiply by square root of 18 over square root of 18. So when we multiply by square root of 18 over square root of 18, this becomes 6 times square root of 18 over 36. 36 is 6, and then I still have 6 square root of 18. 6 divided by 6 is 1. So now I need to figure out what is the square root of 18 and how do I break the square root of 18 down, and that's going to help you arrive at the answer. So this square root of 2 over 2 is fine and wonderful and dandy, but you need to basically keep it simple for the students that might struggle and use square root of 18 over square root of 18. What about this one? If I have a fraction under a square root and they don't divide, so 5 divided by 6 doesn't get me anywhere. So this is not simplified. That's something your students are really going to need help with. You're going to have to make them see that this is not fully simplified because it's actually the square root of 5 divided by the square root of 6. So we need to rationalize the denominator. So I'm going to multiply it by square root of 6 over square root of 6 because that's going to give me a perfect square in the denominator, which is 6. 5 times 6 is square root of 30, and that's as far as I can take that. And the last example is going to be how do we use calculators to help us. So the square root of 311, on a scientific calculator, I would need to put 311 and then hit the square root button. For some reason, that's how those calculators work, and that is no fun. If you're on a graphing calculator, you would need to hit the second button and this. So I would advise actually that you use Web 2.0 and neither of these handheld calculators. If you're in Web 2.0, you just hit the square root button and then you type 311 and then you hit enter. So the Web 2.0 calculator that I use in my other videos is way faster. And so try this in the calculator to see if you arrive at the answer of 37.630.